into the topic of today. So in particular, the dynamical systems that I'm going to introduce to you is highly motivated from the theory of surfaces. So since the homological mirror symmetry conjecture by Kontsevich, there has been a lot of development about this very deep connection in terms of the theory of surfaces and the theory of triangulated categories. So in particular, let's just go through some of what we know from surfaces. For example, given a surface, you can then consider its mapping class group, and then you'll have this mapping class group acting on the surface. And you can consider things like the simple closed curves, and you can consider the intersection numbers between the simple closed curves, and you can pick your favorite metric to put on the surface that you like, and then compute things like length of curves, and in particular compute what is known as the topological entropy, which I'll go through in a bit. So the aim of today's talk is to really go through this side of the story, meaning I'm going to try and go through what triangulated category is in a very, very big sense, and go through, introduce to you some of these notions here, so that we can all really see how we can study triangulated categories in a similar way to how people would study surfaces. Okay, so just briefly, what a triangulated category is, I won't start with the definition, but instead I'll just start with the examples of what you should be keeping in mind when I'm going through this whole talk. So in particular, take A to be an abelian category, and I'll denote comp A with a B as my superscript to be the homotopy category of bounded complexes of A, meaning the objects are going to be complexes in A, and the morphisms are morphisms of complexes, so they'll need to commute. Every single square needs to commute, but I'm going to only consider them up to homotopy. Okay, meaning if the maps are 0 if they're actually non-homotopic. So for those, this will be your prototypical example of what a triangulated category should be. So every time when I'm talking about triangulated category and you have no idea what's going on, just go back and think about complexes. For those of you who are more familiar with algebraic geometry, maybe you want to consider the derived category instead, which has the exact same objects, but now the morphisms are morphisms of complexes, where we formally invert the quasi-isomorphisms, meaning the ones that actually induces isomorphisms on the homology. Okay, so these two are the main examples that you should keep in mind throughout the whole talk. So a triangulated category is in particular an additive category with a shift autoequivalence. So in the sense of complexes, you should really think of this as like cohomological degree shift with a set of exact triangles. So these exact triangles should be closed under isomorphisms. And if you really want to, maybe you can really just think of this for the time being that they are like exact sequences in abelian categories. So in particular, they satisfy a few set of axioms. I won't go through all of them, but I'll just say a few things that are a little bit more important. So the first one is that given any morphisms between two objects, there's always a way to complete it into an exact triangle. And in particular, for the examples that I've gave you for complexes, the way to complete it is to take its cone. So that if you're considering these two triangulated category here, given any map between the two complexes, you can always take its cone, with this map being the inclusion map and this map being the projection map, and that will give you an exact triangle. Okay, and the other one that is probably a little bit more important is also that if I have any isomorphism between two objects, then this triangle here, or this sequence here, is going to be an exact triangle. Okay, and there are a few more properties about these things. So in particular, for example, in a abelian category, these exact triangles is going to satisfy the kernel property and the co-kernel property. But for exact triangles, what you have is just like a weak kernel property and a weak co-kernel property. And what that means is that you have induced map in the kernel property sense, but now the map is not going to be unit. Okay, all right. So before we jump into the dynamical systems and triangulated categories, I'm just going to quickly motivate things from the point of view of topology, or in particular surfaces. So given the surface S, and let me denote C as the isotopy classes of simple closed curve, there are three ways in particular that you can actually compute what is known as the entropy of a mapping class group element. So just quickly, a mapping class group element here should really just be all the diffeomorphisms up to isotopy. Okay, and there are 3 ways in total which are shown to be equivalent that you can actually compute what is known as the topological entropy. So the idea is that entropy should measure what's known as like a mixing complexity. And in particular, if the entropy is very large, then you should think of this as like there's a lot of mixing going on within the surface as I take higher and higher powers of these diffeomorphisms. So there are 3 ways to compute entropy in particular. And the first one is known as what's called the Wood metric. So this guy here is what's known as the Wood metric. And this Wood metric is given as such. So for example, if I consider this surface right here, and if I try and take these 3 generators as my generators in pi1, which is the first homotopy group, then given any simple closed curves as such, I can always rewrite them up to isotopy, so squeeze them around if you like, so that they look like the generators up there. So in particular, for this example here, you can rewrite it so that it looks like this. And the Wood metric with respect to this generator's G is just given by the minimum length of such objects. Okay, and so this is one way to compute it. So basically, you're just saying that, okay, I'm going to take higher and higher powers of a simple closed curve and see how the Wood metric grow, how the Wood length grow with respect to this metric, if you like. The other way to compute it is to use what's known as the intersection numbers. So what this one does is basically you're taking one simple closed curve, the original simple closed curve, and compare it to the higher and higher powers of the action on this simple closed curve, and you see how the intersection number grows. And again, because all the curves are just up to isotopy, all that you're doing is just computing the intersection numbers up to the minimal one. So you try to isotope it so that the number of intersection actually is the minimal one. And finally, the last way to compute it is to compute it according to some sort of metric on the surface, where I use L mu to denote the length according to this metric. So again, you do the same thing. You just take some simple closed curve alpha, and you compute how the length of the curve grows as you take higher and higher powers of the mapping class element. And the big theorem in some sense is that all these things compute to the same number. So they are all the same invariant for the same mapping class element. So what I'm going to do today is to introduce the analogs of these 3 notions in the triangulated category sense and compare them and see how far we can go. Okay, so before I talk about the entropy of endofunctors of triangulated categories, I'll introduce what's like the analog notion of what a generator should be in a triangulated category. So we say that an object is a split generator of a triangulated category, and we call it G, if for every object X that we're given, up to taking direct sums, we can write it as a filtration in terms of the split generator G. So up to taking the direct sums of some object, there exists a finite length filtration that looks something like this. Okay, and if for all objects such a thing exists, then G is a split generator for the triangulated category. And now we can measure the Wood metric, the analog of a Wood metric, which is called the complexity of the object with respect to F, by basically just saying that what is the minimal length of this filtration. So if I take E, direct sum with, oops, that's not an F, that should just be, again, direct sum with any object E prime that you like, what's the length in terms of filtering it by F? And if F in this case, for example, if F is a split generator, then such a filtration always exists by definition. And you can find its minimal length by just really going through the whole thing and find what's the minimal length needed that you can write it down in such a way. And the entropy of an exact functor, which is given by Dimitrov, Hayden, Kazakov, and Kontsevich, is as such. So again, instead of measuring it with respect to the Wood metric, now we measure it with respect to the analog of the Wood metric, which is just the complexity. So you compute this number here, and you need to show that this limit does actually exist, and it turns out that it's also independent of the choice of the split generator G. And this we will take as the definition of what an entropy should be. So it should be the analog of the one that we have in the topological sense. And let's just compute a few examples so that we're all a little bit more comfortable with how should one compute an entropy. So for the first example, let's just work with the simplest one that we can think of, which is just take the triangulated category given by the derived category or the homotopy category of vector spaces. So in this case, basically, if you're more familiar with this, this is really just the graded category. Sorry, this is just the category of graded vector spaces as well, and Z-graded vector spaces in particular. And we can consider the endofunctor taken by just tensoring with R squared. So if you like, really all this does is just taking the vector spaces, and then I'm just going to tensor. Once you tensor with R squared, I'm just going to multiply by 2, if you like. So this is like the categorical notion of multiplication by 2. And it's very easy to see that then with if I take R and I view it as a complex concentrated in degree 0, meaning it's just a complex with R in the cohomological degree 0 and 0 everywhere else, then this should be a split generator. So in particular, if I look at this object here, which is just taking R tensor over R by R2, and I'm doing this n times so that I get to R2n, then we can see that as I take higher and higher powers of things, the way to filter it is really just write it out say that there's 2n pieces of them. Okay? And so what happens here is that, well, it's easy to see that in this case, the complexity or the minimal length of the filtration is exactly how many pieces of R to n for getting it up to the grading shift, if you like, how many pieces of R that I have in my complex. Okay, so in this case, when if I'm multiplying by 2, then I'm going to get 2 pieces, and multiplying by 2 twice, then I'm going to get 4 pieces, so on and so forth. So all that I'm getting is just 2 to the power n. And so now if I compute this limit, it indeed gives me log 2. So all it's saying is that all that you're doing is really just logarithmic, up to logarithmic is just 2. You're just multiplying by 2. So this seems like a rather simple result, and it's something that you might expect. So since I tried to look through some of the talks, and I saw that someone's going to talk about fusion category. So maybe it will be a good idea for me to also give you an example which actually involves such a thing. So I'll denote the fusion category FIB, which is, if you don't know what a fusion category is, all that I'm going to tell you is that it's a semi-simple category, and there's only two simple objects, which one of them is 1, which should be the tensor unit, and the other one is this guy tau here, which you should really think of it as like a category-fied version of the golden ratio. So in particular, when you take tau and you tensor with tau, you get 1 plus tau. So this really is just the golden ratio relation if you view this as something like delta squared is equal to 1 plus delta. Okay, so this should really just be the category-fied version of the golden ratio relation. And my claim is that in this case, the split generator can be taken to just be one direct sum with tau. And if I compute the entropy of this guy here, then all that I'm going to get is the logarithm of the golden ratio, because all that I'm doing is basically just saying that I'm multiplying by the golden ratio in the categorical sense. Okay, so these two examples are actually, in some sense, the examples that are very simple and you can really compute by hand. But as you would imagine, computing entropy for random endofunctors or endofunctors of some interesting endofunctors can be hard in general. So what I'm going to do is I'll just give you a few nice results that has been proven so that you can get a flavor of what people have actually tried to do. So the original author that introduced this notion of entropy, to motivate their definition, they gave this theorem which says that given a surface S and any element in the mapping class group, which is pseudo-Anosov in particular, meaning I won't go through what pseudo-Anosov actually is, but you can really just think of this as saying that if a mapping class group element is pseudo-Anosov, take any curve, any simple closed curve that you like, which is non-degenerate. And if you take higher and higher powers of it, the simple closed curve gets more and more complicated, meaning the intersection number grows very complicatedly, if you like, or there's a lot of mixing going on, is what you should have in mind. And what you can do is consider what is the triangulated category version of the Fukaya category. Don't worry too much about it, but basically you can create some out of this surface, you can create some very complicated triangulated category and consider its induced action on its triangulated category. And when you consider it this way, then the categorical entropy actually agrees with the topological entropy. And in particular, in this case, it is known to just be log lambda, where lambda is like the scaling factor of the pseudo-Nosov map. On the more algebraic geometry side, there's a few results which say something like, if you want to compute the entropy of some endofunctor when you're working with smooth projective varieties, then all that you're doing here is you're measuring with respect to the dimension of the Hom space. So going back to the analogy that we had just now, in particular, you should really just think of these dimension of Hom space as some sort of correspondence to intersection numbers instead. Okay, so when you're computing entropy, then a similar statement from the topological sense works, because now all that you're doing is just taking computing with respect to intersection numbers. Okay, and finally, there's also a result by Kikuta Takahashi, which again shows that the entropy of some endofunctors actually agrees with the one that is induced on the topological side as well. Okay, so seems like I don't have much time. Giving a 20 minutes talk is always hard. But I won't go through too much of this. So the last two structure that I'll just quickly say is meant to be the analog of length of curves and the analog of what, in particular, the analog of what a metric is. So for those of you who are a little bit more familiar with T structures, you should think of a stability condition as some sort of a refinement of the T structure with an extra map called the central charge. And this allows you to give an analog of what is known as the metric on the triangulated categories. So in particular, you will obtain what's called the semi-stable objects, and these are meant to be geodesics. And more importantly, what's important is what's called the Harden-Arrowsmith filtration. And again, in the topological sense, you should think of this as a geodesic rectification of the path, meaning you're given some sort of path and you want to compute its length. It turns out that you can rectify some of these paths so that they're actually given by geodesics. And when you want to compute its length, all that you're going to do is just add up the length of each of the geodesics. And the mass of an object, in this case, is again just going to be given by this analog. Exactly that you're just going to sum up each of the pieces that are actually the geodesics, and you sum up their masses, which are actually the length, the analog of the length in that case. And again, you can now compute a separate thing, which is what's known as a mass growth. Now, you can consider instead that instead of using the complexity to compute this limit beforehand, now we can think of this as, well, how does the mass, or in particular, how does the length grow according to this endofunctor? And given what we know from topology, it's very natural to ask, okay, if we have two separate notions that have some sort of analog in the categorical sense, do they actually agree? So in general, it turns out that they don't, although it is true indeed that there is always a lower bound. In particular, if I compute the mass growth, meaning the limit which is computed using mass instead, it is always a lower bound of the entropy that we define, meaning the one that was computed by the complexity. But for some cases, meaning when a triangulated category contains what's known as an algebraic heart, meaning it is a finite length, finitely many simple abelian category, then these two notions actually agree, meaning we can actually compute the mass growth and we can actually compute the entropy, and they actually agree on the nose. Okay, so that's a very brief introduction into this topic of dynamical systems and triangulated categories. And there's a few, I guess, rather natural questions that you can ask, or some things that you can go home and just start doing as a research project. So for example, pick your favorite endofunctor, try and compute its entropy. That's a very natural thing to do. And you can also ask a few more deeper questions. For example, under what conditions do these different growth rates, the one that's given by the mass growth and the ones that's given by the entropy, what are the other conditions such that these actually agree? And finally, there's also this very famous classifications of diffeomorphisms given by Thurston, and you can ask whether or not there's a very similar classification for triangulated category autoequivalences. All right, thank you for listening, and sign up to my symposium.
Thank you, Edmund, and silent round of applause again. So I'll stop the recording there.